In this live example, we're going to create a program that will determine if a number is a McNugget number. Now here, a McNugget number is defined as a number in which we can order exactly that many chicken McNuggets at McDonald's. So for this exercise, we're going to assume that McDonald's sells chicken McNuggets in boxes of 4, 6, and 10. A lot of them also sell 20-piece or 40-piece nuggets. We're going to ignore those because we're going to see 20 and 40 are just multiples of 10 anyway. So assuming we can only order boxes of 4, 6, and 10, is a number n achievable exactly by ordering a combination of boxes of 4-piece boxes, 6-piece boxes, and 10-piece boxes. So for example, 8 is a McNugget number because we could order 2 4-piece boxes and we can get 8. Also 14 would be a McNugget number. We could order a 10-piece box and a 4-piece box. We could actually also order 2 4-piece boxes and a 6-piece box, and that would either combination would work. So all we're looking for here is we want to know, can we order a combination of these piece boxes to get a specified number? A little bit more complicated version of this would be, do we want the least expensive way to get the number? Well, then we would have to factor in how much does a 4-piece, a 6-piece, and a 10-piece box cost. So we're not going to consider that. So is it achievable with a combination of 4, 6, and 10-piece boxes? And we want to know what's the largest n that this will not work. So what's the largest number of pieces we want exactly where no combination of 4, 6, and 10 will get us exactly there? So for example, like 5 is not a McNugget number. There's no combination of 4, 6, and 10 that we can get exactly 5. We can get order of 6, but we have 1 too many. Okay, so before we get into programming this up to solve it, one, I'm doing this live. I've not pre-made notes or anything, so you're going to be going with me on this journey of figuring out how to program this. I'm specifically going to be using loops to achieve this, for loops in particular. Even though there are more efficient ways to do this, we could use linear programming outside the scope of this course to do it very efficiently. But I want to use for loops, and we're going to be using basically what I'll refer to as a brute force method to do this. Again, it's not meant to be the most efficient, but more of an application of loops, and so we can see some tricks we can use and some techniques we can use to turn this problem from a statement into a solution. All right, so jumping into the MATLAB here, I just copied the problem statement from the slide in, and I'm going to solve this one as a script. We could alternatively make a function where we can give it a number and it's going to tell us, is it a McNugget number or not? But for right now, I'll just do it as a script. We could always convert it later if we wanted to for this. All right, so when reading this, what we want to think about is very often it's going to be helpful. If we wanted to do this just by hand on paper, what would we do? So if we were given a number, again, let's say 8, we could say, all right, is 8 a McNugget number? How can I combine 4, 6, and 10 to get 8? So in this case, we might say, well, 10 is more than 8, so I shouldn't be using any 10-piece boxes. I could use one 6-piece box, but then nothing else is going to work, so that's not going to work. I could use a 4-piece box, since that's less than 8. I could add another 4-piece box to that, and I'll get exactly 8. Or we could try a number like 7. Okay, 10 is bigger, so there's no reason to even try that. 6 will divide into 7. So I could try one 6-piece box, but then even adding the smallest one of 4, it's going to be too big, so that combination is not going to work. I could try a 4-piece box, but then again, if I add a 6 or a 10 or even a 4, that's too big, so 7 would not be a McNugget number. But kind of a naive way it'll work for this is going to be, what if we just try a bunch of different combinations of 4, 6, and 10 and see, is there a combination that's going to work? What makes this problem both more difficult and in some ways more simple is that I can only order an integer number of boxes. So I can't order 1.5 boxes of 4-piece nuggets to get 6, let's say. I have to order exactly 0, 1, 2, 3, 4, 5. So this is an integer problem. So again, if we wanted a more elegant way to do this using linear algebra, we could use integer programming to do it, and we could do even very complicated combinations with lots more types of piece boxes very, very efficiently. When I go through my steps to do this with a brute force method, it is time consuming because we're going to be trying a lot of combinations that aren't going to work, which is going to waste a lot of the computer's time. But it's going to be, in this case, a small enough problem. It's not a big deal. Okay, so what we can do is we can try for any number. I'll just arbitrarily put one out for now. Let's say I want 14 like I mentioned earlier. And I'll make this more robust as we go along. So let me just test is 14 a McNugget number. All right, so there's not a unique solution to this as I described earlier, but all we're looking for is, can we make this combination, not what's the most efficient way or what uses the fewest orders, just is it achievable? So what we can try here is a lot of different combinations. So I'll use, as we'll see in a second, for loops for this, because I want to try, well, for example, what if I put together 0 boxes of 4, 0 boxes of 6, 1 box of 10? Does that work? We'll see it won't. What about 1 box of 4, 1 box of 6, 0 boxes of 10? Well, that won't work either. What if I tried 1 box of 4, 0 of 6, 1 of 10? That does work. So really we're just going to kind of exhaust the combinations we could have of these boxes until we find one that works, or possibly we won't find one that works. All right, so I'm going to try a bunch of different integer numbers of boxes. Let me do I'll start with the biggest and go to the smallest. The order really isn't too important, but I'm going to say I equals, so I is going to represent the number of 10-piece boxes I want to try. All right, so I'll note here, I do want to start I at 0. Usually that's not the case. I will explicitly put 1 there, even though that'll do the same thing. I will start I at 0. What we're going to see, the way I'm going to solve this, is I'm not going to be indexing anything. So starting my variable at 0 is not going to be a big deal. If I'm going to use I as an indexing variable, then generally, yes, I do want to start it at 1. So this is a case where I can kind of break the rules. All right, so I represents how many 10 boxes I want to use. Right here, I'm just saying I'm going to try using 0, and then 1, 2, 3, 4, up to 10 of them. I'll modify this in a minute. I just want this to get started here. So then I'm going to say, all right, well, that's how many 10-piece boxes I'm going to try. What about 6-piece boxes? Well, I can select the number of 6-piece boxes independently of the number of 10-piece boxes. So for this, I'm going to say, well, if I use 0 through 10 6-piece boxes. Right, so what I'm doing here is I'm using nested for loops because I want to try all these different combinations of 4, 6, and 10-piece boxes. Now, a lot of them, most of them are not going to work, and that's what is going to contribute to the inefficiencies of this brute force method where I'm just trying a bunch of things and seeing if any of them work. But it will kind of exhaust the possibilities, so it will find it if it exists. So k will be the number of 4-piece boxes I want to use. So again, I'm just going to arbitrarily say up to 10 of them. And like I said, I'll come back and clean this up a little bit because I'm going to be wasting a lot of, there's no reason, for example, at least on the 14, if I wanted to make 14 nuggets, there's no reason to even try 2 20-piece boxes or more because automatically none of them will ever equal 14 because it's already 20 or 30. So this could be a lot of wasted comparisons as we'll see. So I'll come back and clean that up. All right, so this is going to, with these triple nested for loops, try all of these combinations of 4, 6, and 10-piece boxes from 0, all zeros, which clearly won't work, to trying 0i, 0j, 1k, then in the inside loop, 2 times k, 3 times k, etc. So what I want to do on the innermost loop is see, once I set an ij and a k, how many nuggets in total do I have. So if I order, again, let's say I is 1, J is 1, K is 1. If I order a 4-piece, a 6-piece, a 10-piece box, how many total nuggets do I have? Well, since I is the number of 10-piece boxes, I'll have 10 times I plus 6 times J plus 4 times K nuggets when I'm in the inside of the loop. Okay, and let me space those out a little bit. So what I want to compare is that number to n. So again, I'm just going to try 14 for now. We'll see how I can expand this later. So I want to know really, are those two things equal? Is the number of nuggets I desire exactly equal to the number of nuggets I ordered on this attempt? When I order I 10-piece boxes, J 6-piece boxes, and K 4-piece boxes. So if that's true, I am going to set, I'm going to create a new variable called MCN, McNuggets, and I'm going to set that to 1. All I want to keep track of is big N a McNugget number? So if there is a combination of 4, 6, and 10-piece boxes I can order that's exactly equal to N, then yes, it is a McNugget number. And otherwise, it's not a McNugget number. Now, what I'll be careful is I don't want to do this. So I don't want to set that MCN equal to 0 because, at least the way I have it programmed so far, if I say that it's equal to 0 otherwise, it could come down inside this loop, find a combination of I's, J's, and K's that works, and then it's going to set the McNugget number to 1. But at least the way I have it at the moment, it's going to keep doing these loops until all of them are satisfied. So if it comes a subsequent loop and it tries a larger value of K and it does this calculation and that combination doesn't work, it's going to say, oh, no, this is not a McNugget number. But we actually already determined that it was a McNugget number. So once we find a combination that works, we don't want to accidentally overwrite it with a 0. So we'll see in a minute how to fix that. Okay, and I'm going to close all of my loops here. All right, so this is the very, very first version of this, and let me, at the end, I'll display MCN. Okay, so that should be a 1 if this works. So let me try running this very early version of this. All right, so we have an issue here. Oh, it's in how I did this K at the moment. All right, now let me rerun this. Okay, so it did work. Now what the code is not doing is remembering the combination that worked. We're not being asked in this problem to do that, but that could be an extension that we would be interested in, is how many of each box should we order so that we get exactly N chicken nuggets. But right now we're not saving that information. Again, we're not saving what the cost would be or things like that. So if we look at our workspace here, it ended because I got up to 10, J and K got up to 10 as well. And it did find that it gave us a 1. Yes, this is a McNugget number. What happens if I try one that we didn't have when we kind of thought about it? 7 is not a McNugget number. All right, so if I run this, it's giving me an error at 24, display MCN. If I look in the workspace, MCN is not present. I'm trying to display something that's not present. Because I didn't put in the code that else, making MCN 0, when I get down here for something that's not a McNugget number, it's trying to display the value of MCN, but I never defined it. So what I do want to do here is I'm going to assume up front that something is not a McNugget number until I find out that it is. So I'm not having this else in here, but the default assumption is not a McNugget number. Right, so that 0 will get overwritten if it discovers that it is a McNugget number, but if it never gets to this if statement, then MCN will just remain 0, and therefore it will not be a McNugget number. All right, so now if I run this for a known non-McNugget number 7, it returns a 0, as should be expected. All right, so before I go, so this works for just one value of N. at a time. So again, if I have like, is 15 a McNugget number? It says no. Is we know 20 should be because we can order two 10-piece boxes, and we get a 1. Okay, so it works for one number at a time. This is part of the question we want to answer. It's answering for a specific value. Is it a McNugget number or not? We can answer that. However, again, it's going to be doing this inefficiently. And also, if we try a really big number, let's just say 10,000 here, this should be a McNugget number. We can order a bunch of 10-piece boxes, and it's going to add up to 10,000. However, when I run this, it returns a 0. And that's because the way I have this upper limit on I, the number of 10-piece boxes, I arbitrarily said 10, because I don't necessarily know up front what the combination is going to be. So I have to put some upper limit. In this case, 10 is not enough. But for a low number like 7, well, 10 is way too many. There's no reason to be trying such large numbers. So before I do this in another loop to try a bunch of different McNugget numbers, I can make this more efficient. So really, let's go back to like 14 and run this. Like I said earlier, there's no reason to test I equal to 2, 3, 4, 5, because it's none of those are going to work. It's a waste of the computer's time. So in this case, when it's 14, it's worth trying 0 boxes of 10 and 1 box of 10, but nothing larger than that. So what I can do is I can change dynamically what this upper limit is based on the value of n. So I can put in a little bit of thought beforehand, even though it is going to ultimately just try a bunch of different combinations here. So what can I do? So for like 10, what if I say n divided by 10 is 1.4? So that is going to tell me that there's 0 is worth trying, 1 is worth trying, but 2 is not. So the upper limit here, I can make n over 10. But I want to be careful here because I don't want to, this actually should work because it's a for loop. But really what I can do here is, instead of simply n over 10, which is going to be a decimal, I want to just make it an integer, so it's a little bit cleaner. I'm going to use floor. So what floor does, it's going to be what is the closest integer less than this value, as opposed to ceil or ceiling, which is what is the closest integer larger than this value. So it's different than round, because round will go to the closest integer. Floor will always go to the closest integer less than this number. Right, so this will now, like when n is 14, it's only going to run this outermost loop for 0 and 1, and then it's going to stop because we know everything else is going to be a waste. And I can do similar ideas for 6-piece boxes. Again, with 14, I can try 0, 1, and 2 boxes, but there's no reason to try 3 boxes of 6 because that's 18. It's going to be too large. So this I can also modify, and it's going to be a little bit quicker here. And actually what I should have done is I can time this, and we can see it's probably not going to make much of a difference, but we can see what that difference is. So let me just go back to the way it was for a time comparison here. All right, so kind of this very brute force way, just arbitrarily declaring it 10. And if I run this, it doesn't really take that long at all, so we're probably not going to notice a big speed up yet. But we will get a more appreciable speed up when we try this in a bigger loop here. All right, so this is where I'm always going up to 10. Now let me use the slightly more efficient way where I'm going to limit the values on i's, j's, and k's to even try. And actually the other benefit of this is we're going to see that this will work for 10,000 nuggets, because now the cap, the largest value I can take is not going to be too small. It's going to always be big enough and small enough for it to be efficient. Okay, so make that 6. And for the 4-piece, again, I can do the same idea there. All right, so I have a much more intelligent way of trying the IJK combinations here. So now if I run it, we really can't tell, honestly, the speed difference right now because it is such a kind of small problem at the moment. So that's not going to help us too much. But a benefit is if I put in, I want to order exactly 10,000 nuggets for everyone on campus, it now is able to, it takes a while here, but it is going to be able to determine that yes, 10,000 is a McNugget number. All right, so it cranked through all those combinations, and it did take, I'll say, kind of quite a while here. It took about 12 seconds for it to discover that yes, 10,000 was a McNugget number, because we are brute forcing all of these combinations here. Again, there's other ways we could introduce some speed ups here by just putting in some simple logic of combinations not to try. Like if it's exactly a factor of 10, well, then we can do this really quickly. So we could circumvent some of that. Okay, let's go back down to kind of smaller numbers here, back to like 23, all right, not a McNugget number. All right, so the first part works and we have it a little bit more efficiency there. We want to try what's the largest value of n for which we can't get exactly that many nuggets in our order. All right, so let me expand how this works. So instead of just trying one value of n at a time, I am going to make n my, let's say, the upper limit. So I'll just try 25 for the moment. So I want to try I want to test all the numbers from 1 to 25. So I'm changing its definition here. Upper limit of McNugget number to test. So I want my code to test is 1, 2, 3, 4, 5, etc. a McNugget number. Right, so I will make another for loop that goes from, let's say, 1 to n on the outside. Right, so this way I can keep trying different tests over and over again. And now MCN, instead of, I'm going to have a whole list of values here. So instead of a single 0, I'm going to say it's zeros n by 1. I'm just going to run up to here for now. And I spelled zeros wrong. Okay. All right, so MCN is now, I'm going to keep a track of, for each number, was it a McNugget number or not. So I'm going to make that same assumption as before. I'll assume it's not, and we'll see what happens. Okay, so MCN is my list. I'm now going from n equals 1 to n. Let me indent this properly. Now I have to be careful because m is now the McNugget number I'm testing, not n. So I actually need to change all of these values in here. All right, so what this is going to do when it enters that first for loop, it's going to say is 1, m equals 1, is 1 a McNugget number. And it's going to test this and then return, it's going to save a 1 if it is and a 0 in this spot if it's not. All right, and then it's going to go all the way through the loop, and then it's going to go to 2. Is 2 a McNugget number? Because m is now set to 2, and now it's going to try 2. So let's see how this works. All right, so let's see what happens here. So it gave me an error, MCN. It's it ran without an error, but it's not giving me a list of numbers here. What we need to remember to do here is when I am saving that I found that something is a McNugget number, what I forgot to do was index it. So this MCN, what I'm doing is I do originally make it this list of numbers, this vector of numbers in 14, but then I'm overwriting that list with a scalar in 22. I need to index this. I'm going to index it on m. So is the mth attempt a McNugget number or not? Now, if I run this, let me just do it smaller here, just to 10. Now we see that MCN is a list of numbers. So it's saying that the way I'm interpreting this is the first one is 1 a McNugget number? No. 2, 3, no. 4, yes. 5, no. 6, yes. 7, no. 8, yes, because I can order 2 4-piece boxes. 9 is not. 10 is. All right, so now I can try a bunch of different numbers and see, do I have a McNugget number, or which ones are McNugget numbers. I want to display this horizontally just so it's a little bit easier to see here. All right, so I have a row now that is no, it's not a McNugget number, or 1, it is a McNugget number. All right, so I'm closer to solving my problem. Let me go up to 25 and just rerun this. All right, so now it's trying 1 through 25, testing if they're McNugget numbers. So we're finding a lot of values that aren't in here. There's a lot of zeros. Let me just go up to 50. Right, still a bunch of values that we're finding are not McNugget numbers here. And ones that are. So as we keep doing this for larger and larger values of n, let's say 1,000, we're going to see that we kind of get this repeating pattern happening when it runs it here. So it actually turns out for this combination of nuggets, since we can only do 4, 6, and 10, since at least with this combination we can only order an even number of nuggets. There's no way to get an odd number of nuggets here. We see we get this repeating pattern happening. So it's actually fairly limited with this particular example since we can't order like a box of 5 or 3 or 7 nuggets, that there's no way that any odd combination is going to work. However, we see that the even ones where we get this 1 repeating, generally this pattern is true. So there does exist some combination to get, it looks like, almost every even number of nuggets. However, there is no way to get any odd nuggets here. So this particular box combination turned out to not be as interesting as I thought it would be, but we are still doing the same tests. Now again, as an extension of this, if you wanted to make it a little bit more interesting of a problem, is even though, let's say 1,000 is certainly a McNugget number, we could expand our code as an exercise for you of what's the least expensive way to do this. Because the per nugget price, let's say, of a 10 piece is less than a 6, is less than a 4 most likely. So a 1,000-piece nugget is going to be cheapest if we just order 100 10 pieces rather than a lot of, let's say, half 4 pieces and half 6 pieces. So that, in addition, you could put into the code and then see what's the least expensive way to find a McNugget number. And then there's other speed ups we could put in here as well. So for example, let me do this so 1,000 took about 4 seconds to run. Let me run it again just to get a good time check here. All right, so again, it took about 4.2 seconds to run up to 1,000. I can put something in here, and there's better ways to do this also. I can put a break here. So what this is going to do is, if it discovers that this is indeed a McNugget number, what break is going to do is it's going to exit whatever the innermost loop is that I'm in. This will give us a little bit of time savings, not too much, because it's a triple nested for loop. So if it discovers an IJK combination is indeed a McNugget number, in this example at least, we don't care about how many boxes it took. We just want to know, is it or is it not a McNugget number? So once we know it is, there's no reason to keep testing a lot more Ks because we already have a 1 here. So what break does, it'll break out of this for loop and go into the J. So we're still wasting a good amount of time there, but we're going to save some iterations by putting this break in. So if I run this, we might see a little bit of a speed up as it's trying fewer combinations, and we do. We're going to get the same exact results. We do get them a little bit quicker. So I'll just put in a couple more speed ups here. Or examples of speed up here to optimize the code a little bit while we're still sticking to the spirit of the problem. Really what I can do here is I'm going to use a flag, and we'll see what this will do in a second. So the flag will indicate if McNugget number was found. Okay, so this way I can use the breaks a little bit more effectively. If I found that little m is a McNugget number, I'm going to set it equal to 1. I'm also going to make this flag equal to 1. Actually, I could probably do this more efficiently. I could just use MCN of m as the flag itself, but I'll do it this way for now. All right, so, and actually I'll do this here. So every time I change my little m, I'm going to reset the flag to 0. So what it's going to do, it's going to say, oh, I've discovered this is indeed a McNugget number. For this example, there's no reason to keep testing it. It already is a McNugget number. If we find another combination, that's fine. We don't care about it right now. So I'll set the flag equal to 1. So what I'm going to do then is, after this if statement, I'm going to check is flag break. Right, so it's going to look for flag. If flag is true or 1, this is going to do the same thing as this. I'll put the equals 1 here for now. So if that's true, it's going to break, which means it's going to exit my innermost for loop because I don't need to test anymore, and it's going to go to my outer next for loop. But again, I can actually do this test again when I'm in the J loop, because again, if I found that flag was true, there's no reason to keep trying additional J values either. And same thing is true in this outermost loop. Right, so once it's found to be a McNugget number, I'm going to break out of my K loop. Then I will also break out of the J loop. No reason to keep testing different values of J. And then that's what this if statement will do. And then in my I loop, again, once I find it's a McNugget number, I can escape the I loop. There's no reason to keep trying different combinations. Then it's going to go to the next value of M. It will reset that flag to 0, and it'll do this process again. So we will find the exact same results, but we should find it even faster now because we're not wasting as many iterations. And we see indeed, look, the time dropped again to 2.7 seconds. Now that I put in these additional pieces since I found my result. So I can put on these extra little bells and whistles. I can optimize the performance or improve the performance a little bit, even though it is doing this exhaustive test. Again, just as a note, if I wanted to find the least expensive way to do this, I wouldn't want to be breaking out of all these loops because there might be multiple ways I could build my boxes to get my desired value of nuggets, which one way might be cheaper than another. So maybe I don't want to do these breaks in that case. It turned out using the actual boxes available at McDonald's, the 4, the 6, and the 10 piece was not that interesting. So just as a last piece here, let's make it a little more interesting and pretend like they sell boxes of 4, 7, and 10. So now we will be able to get odd numbers. So I just want to change all these 6s to 7 here, and we can see how that works. So at least we get a better result. Okay, so if they sold it in boxes of 4, 7, and 10, now we want to see what would our McNugget numbers be under this case. Because now we can't simply add the 4 and the 6, which was the 10, and that's what really limited our choices. So we can have 4, 7, and 10. So same thing here, I'm going to try up to 1,000. Right, so running this actually runs quicker because as soon as it detects it is a McNugget number, it stops with all these breaks here. So we see actually it doesn't take much time at all. So now we're seeing a lot of more McNugget numbers, obviously because we can have even and odd values. So the last part of the problem was we were interested in what was the largest value of n that was not a McNugget number. What's the largest number of exact pieces we wanted that we could not get from some combination from now 4, 7, and 10. So what we can do, we have all these ones here. Let me see where is... So I want to find all the locations where MCN is still 0. And I'll print that out. So showing this in the display, I don't really need to do anymore. So let me run this whole thing. All right, so now the only values that we can't get, we see are 1, 2, 3, 5, 6, 9, and 13. So actually the largest number of nuggets we want that we can't get an exact mixture for with this combination of 4, 7, and 10, we actually get 13. I only tested numbers up to 1,000, but presumably that's going to hold true. Let's see if I keep increasing this to larger numbers just to make sure we're not missing any. Testing all the way up to 100,000 nuggets. I'm not going to go any further because it does take a little bit of time there. So even if we wanted 100,000 nuggets for all of our friends, that would be possible, or any number up to 100,000 except for this list here would be a McNugget number. So one last thing is, I'll try one more. What if they sold in boxes of 4, 7, and 15? Let's limit our selection just a little bit and see if we get more McNugget numbers now. Let me take this down so it doesn't take quite as long. All right, so we do get more McNugget numbers. I'm going to undo those changes back to 10. We did get more numbers, but still, we find there's actually not that many non-McNugget numbers with these 3 boxes that we can select from. So one last time, these are the only non-McNugget numbers that we find.